video we're going to be talking about 3.4 multiplication concepts, algorithms, and estimation. And I have to say that I think of all of the topics that we cover in pre-K education, multiplication might be my favorite. It's second only to introducing fraction concepts. And so I'll talk more about fractions once we get to that section. But I just think this transition from additive thinking and reasoning, so where we add on a constant amount, to multiplicative reasoning is just like this really fascinating snippet of children's thinking. And so this video is going to follow roughly the sequence that we had in addition and subtraction, and we'll have in division, where we're going to start with the meaning, we're going to look at some models, and then we're going to look at some mental calculations and things like that. But just like we had our and, remember our discussion about et, that ampersand, which gave us the ampersand and the addition sign. I'm going to start with a little bit with the meaning of multiplication. And so to do that, I'm going to go ahead and start with this Common Core State Standard Math Content 3. So this is third grade. Operations. It says interpret products of whole numbers. For example, interpret 5 times 7 as the total number of objects in 5 groups of 7 objects each. And so it's really important that we know that 5 times 7, we're going to read as 5 groups of 7. And this is really important because that means when we draw a set model, we're going to have 5 groups with 7 in them. So 1, 2, 3, 4, 5, 6, 7. 2 of those, 3 of those, 4 of those, 5 of those, 6 of those. Nope. One too far. 5 of those. 5 groups of 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Which I probably could have typed in beforehand. But whenever we see 5 times 7, we're going to think 5 groups of 7 objects. And that's because it gives us a consistent way to interpret a product. And it also because it's one of the standards that eventually you'll have to teach. And so, generally speaking, we can talk about our multiplier, m times, so you'll see either a dot, so m times n equals p, or we see our traditional x, m times n equals p. I would say depends on the textbook that you're looking at, which one they're going to use. I tend to use the dot just because once we get to algebraic thinking and we have variables, x is our go-to variable, and so it's hard when you have like x times 5 and you would have x 5. But just like we had our minuend minus our subtrahend, we have a multiplier times our multiplicand, and together they give us our product. And so whenever we're talking about the meaning of multiplication, I want us to think about we have m groups of size n. I wrote an n there. Size n for total p. So we have our m groups of size n, which together gives us p as our product. So when we think of 3 times 5 equals 15, you could think of this, we have 3 plates with 5 cookies on each plate. How many cookies are there in total? So we have 3 plates. Oh, I don't have my pen out. 3 plates with 5 cookies on each plate. How many plates? Well, I already told you how many plates. There are 3 of them. How many cookies in total? And the answer is 15. Let me go on a trip. We're going to go up to the corner. because we have 3 plates, each with 5 cookies for our picture of our product. And you know what? I might even say, draw a circle around that. Kind of reinforces that's that total amount on your 5 plates. Let's move me back. Okay. So m times n equals p. Multiplier times multiplicand equals product. And it's really important that we're comfortable with number of groups times size of each group for total number, because once I get to division in our next video, I'm going to very heavily use this definition, m times n equals p, when I discuss division. And the reason for that really is twofold, right? Like we saw with addition and subtraction, which were inverse operations, and our definition of subtraction depended on our definition of addition. Our definition of division is going to depend on our definition of multiplication. And so our definition is that 3 times 4 equals 12. We have 3 equal groups with 4 dots in each group, which gives us 12 in total. And so if we want to think of multiplication as repeated addition, 3 times 4 is the same as 4 plus 4 plus 4, because we have 3 groups, and 4 is the size of each group. And so, I don't even know what happened to my slide there. Yes, I do. So we'll ignore that. So it says for any whole numbers a and a natural number n, if we have n times a, we have our, I don't know what those numbers are, so we have a plus a plus a plus a last a, and in total that happens n times. I don't know where to be. I'm always in the way. I'm just going to go right in the middle. So n times a, we can write as a plus itself n times. So just like 3 times 4 was, so this is our n, that's our a. So we have 4 plus 4 plus 4, 3 times. So just trying to give you a concrete representation of that definition. All right, go back to the corner. So that's our meaning. We're going to think of multiplication as repeated addition, where we have n groups of a given size m for a total product p. And so I want to tease apart the models and our processes here, because there are 4 models that we often draw upon when we're talking about multiplication. That's whether we're talking about the set model. So again, that's like our picture with the cookies and the plates. Repeated addition model, which I started to show you there, but we'll often use a number line. Array model, which we use rectangles, because that then leverages some knowledge that we would be concurrently learning about geometry. Or rather, that serves as the foundation. An array model serves as the foundation for the area model, which draws on our connection to geometry. So set model multiplication can be thought of as adding the multiplier copies of the multiplicand. And now let's jump back a couple slides. So it says 4 copies of 12. So that means multiply m times n. So I won't jump back because we just said that. M times n. So if m times n equals p, we have 4 times 12 equals p, which means we have 4 groups of 12. So we have 10, 11, 12, 10, 11, 12, 10, 11, 12, 10, 11, 12, and there are 4 groups. And so we put those together, 10, 20, 30, 4, 2, 4, 6, 8, 48. And so we can use a concrete model like here where we have units and longs. And we can think of it as physically bringing together 4 sets of that size, 4 groups of that size multiplicand. Repeated addition. So if we have 5 times 4, and just to never stop saying it, 5 groups of 4, we have 0 to 4, 4 to 8, 8 to 12, 12 to 16, and 16 to 20, which means 5 groups of 4 is 20. So 5 times 4 is 20. Because we can think of it as adding itself multiplicand times. M can be thought, or we can think of P as adding M together. Nope. I was thinking of adding. So see, just like me, go ahead and write M times N equals P. We're adding the multiplicand N added M times. Because it's easiest for me when I'm looking at this to always go back, M times N equals P, M groups of size N, and that way I can translate between that and each of our models. If we think of 5 times 4, we have here 5 groups of 4, and these are, I can't even think of what these are called, but they might be Cuisenaire rods, but for some reason I feel like those are for fractions. But anyhow, these are your number rods. That's what they're called, number rods. So don't always look for the difficult name. So we have 5 groups of size 4. And then by layering with that 2 rods that are 10, that tells us that 5 times 4 is the same as 2 groups of 10. Right? And once we're comfortable with composing and decomposing numbers and thinking about factors, which we'll talk about in a number of sections, we have 5 times 4 is the same as 5 times 2 times 2, which is the same as 10 times 2, which is the same as 2 times 10. Right? And so just like we have associativity and commutativity and things like that, we're going to talk about those in a couple slides. But once we start to use these physical models where we have these rod lengths, we can see these really interesting patterns and convince yourself, why is it that 4 times 5 is the same as 2 tens? Well, we know 4 times 5 is 20, and we know that 2 tens is 20, and so those numbers agree, but why are they the same? Well, you need fractions, but it's because 2.5 fours are 10, right? And 2.5 fours are 10. And so that's exactly where those tens are happening. A repeated addition, I just want to show you, in addition to a number line, you can also have number rods. And with number rods, because you don't have this general endless number line, you would have to use these 10 length rods and put them together and see that, well, that's 20. Right? And we can see that that's relatively easily 20 because that's just place value, 1 plus 1. But that gives us our equivalence. Now our array model, multiplication being thought of as an array of objects. So here we still have 4 groups of 5. And so groups are M corresponds to the number of rows. So M and rows go together, and N goes with the number of columns. So in other words, you can think of it this way. We have 4 rows of 5. But then we start to see, well, if I have 4 rows of 5, if I just kind of rotate it, and I draw my rows a different way, I have 5 rows of 4. circle this way. We have, go on a trip, we can already start to see that 5 times 4 is the same as 4 times 5, right? And that's called commutativity. And so if we have m rows times n in each row, that n corresponds to the column. And then there we were thinking physical counters. We had 5 of them in each row. The area model is starting to think of a grid. And so we wouldn't necessarily have to fill these in. And if you were to draw it, you would say we're given 4 times 5. And you can split that into 4 rows. And then I have 1, 2, 3, 4, 5 there. And we could count 1, 2, 3, 4, 5, 20, right? There are 20 of those there. And so you can either think of them as the squares. Another way you can think of it is at these corners. So counting intersection points, but rather, right, we have to be careful because if we count this first corner and the last corner, we end up with 1, 2, 3, 4, 5, 6, 12, 18, 24, and 30. So I would generally say, don't think about our points, but counting our numbers of squares, right? So you just have to be careful in how you're counting them. If you want to count that way, so that means from left to right, I need 5. And if I do 1, 2, 3, 4, 5, I can't go all the way. And if I count just the inside, 1, 2, 3, 4, that's not quite enough. 3, 4, 5. It's like I don't have anything other than an arbitrary reason for why you might look at just these intersection points. Especially because then we end up counting just 4 wide and 5 tall. And so think about that. That can be some extra thinking time. How, if you were going to count the dots, would you count them here, knowing that we need to get 20, right? And so this is where I would say, just count the squares. All right, so those are our models. So we have the set model where we had our number blocks. Let me move back to the corner. Where we have our groups of a certain size, where we had our m groups with n of our number blocks in them. And then we go ahead and combine them and count the total. And then we switch to repeated addition, which was on our number line, or we also showed it with our number rods. And then we looked at our array model, where we had 4 rows with our certain 5 in each of those, and those were still items. But then we switched to the array model, which is slightly more general. We don't have to draw on those circles, and we're counting squares. So in terms of algorithms, we have partial products. And so the partial product algorithm relies on that meaning of the area model. So if I have 25 times 15. Remember, our array model said we would have 25 rows with 15 in them. And nobody wants to write 25 rows with 15 dots. Nobody has time for that. And so what we do when we complete that is we're like, okay, well, let's use place value. So you can almost call this partial place value products. Because I'm going to split this into, let me pick a different color, 20 and 5 and 10 and 5. And can I fix that. 20 and 5, and so the first thing we do is 20 times 10, which is 200. 20 times 5, which is 100. 10 times 5, which is 50, and 5 times 5, which is 25. And then we say, well, it's 200 plus 100 plus 50 plus 25. And now we have relatively straightforward place value addition. 5 ones, 7 tens, and 3 hundreds. So if you take your handy dandy calculator out, and into it you type 25 times 15, you do in fact get 375. We can also use a concrete model really to reinforce place value, and we end up doing something similar when we get to algebra, when we start thinking about factors and completing the square and things like that, so things you've heard before. So what we have is 23 times 14. That's the question, 23 times 14. And so we have 10, 10, and 3, and 10, and 4. And so actually, I'm going to argue that that's not 23 times 14. It's, we have rows times the size, so we have 14 times 23. And we can do this by place value, just like we would have with the area model. And so this is where I'm gonna now write over it, and it's immediately going to get harder to see. I apologize in advance. We have 10 and 4, and then 20 and 3. So we have 10 times 20. It's 200. 4 times 20, which is 80, right? And we can see the 200, and we have a flat here, and we have a flat here. And here we have all of these rods. Here we have 3 times 10, or 30. And here we have 4 times 3. And see the 4, right? 1, 2, 3, 4 times 3 is 12. And so each of these parentheses is really the multiplication that's happening right above it. So we have 200 plus 30 plus 80 plus 12. So we have 200 plus 110 plus 12, 310, 322. Right, and so the advantage of, say, this model over the area model, certainly in terms of writing and doing, is substantially more work, but this very literally reinforces place value. And so you would use this with a student that's struggling, particularly once you get to multi-digit multiplication, because, right, this is totally manageable if you have like 4 times 3, right? And just have your blocks there, and you have 4 groups with 3 blocks in them. Put them together, they can count to 12, stick them together, get a rod and 2 longs, right? Like that, relatively straightforward. But once you're getting to 14 times 23, which is substantially more labor in terms of working with a concrete model, you would show this for the student that needs a little bit of extra help. And because of that, you can see how that starts to transition us to the standard multiplication algorithm. So if we have 4 times 12, 4 times 12, and this is where I'm going to disagree with the book. This is not 12 times 4. 12 times 4 would be 10, and we have 4 of those, because we have 12 groups. I'm not going to write them all, but 12 groups of 4. So we have 4 times 12, and we can look at place value. 4 times 10 is 40, 4 times 2 is 8, that's 48. So just like we do, 4 times 2 is 8, and then 4 times 10 is 40. Right, I don't want us to think about And let me bring up a whiteboard. So if we have 4. A way you might hear this explained is 4 times 2 is 8, add a 0, 4 times 1 is 4, just add down the columns, 8 and 4, so our answer is 48. I don't like that explanation, so let me cross those out. What I would much rather hear is we have 12 times 4. 4 times 2 is 8. So that's 4 times 2. And then I have 4 times 10 is 40. 48. Right? That's how I would much rather us think about, oh, I wanted to screenshot that, and instead I minimized it. Oh, it's because I need to hit those buttons. There we go. Because that's not a slide I have, I'm going to save it. Because this left one is procedural. You do this, you add a 0, you multiply this, and you just keep going. But on the right, what we do is we reinforce the fact that what's happening is we do 4 times our 1s and then 4 times our 10s. 4 times 2 and then 4 times 10. To get 48. Okay. Now another process that became more popular in the mid-2000s was lattice multiplication. And so here we have 14 times 23. And you can see all of the work is over here, but let me go ahead and work it out. So 14 times 23. So 1, 4, 2, 3, and so you set it up this way. So first we'll do 4 times 2 is 8, 4 times 3 is 12, 1 times 2 is 2, and 1 times 3 is 3. And then we add down the diagonals. So we add down this away, we get a 2. This away, 8, 9, 10, 11, 12, we have a 2. And we carry a 1 to our next diagonal. 1 plus 2 is 3. And we have 3, 22. And now why does this work? Why can we do this? Well, 14, 23, 2, 8, 3, 12. Notice all of those are the same numbers we see. We see our 3, our 8, our 12, our 2. And so this works because of place value, and this adding down the diagonals is just a matter of, oh, except I did something wrong, didn't I? I need this to be 10 plus 4. So that's 200, and that's 30. 20. Whew. I was like, that does not add up, because now we have 200 plus 80 plus 30 plus 12. There we go. And so, given the choice, I would still go back to my array model, or my area model. Let me screenshot that too, or I'm going to lose it. I would go back to this model over lattice because, just like with the standard algorithm, where I write a 0 and then a 4 for 40, instead of thinking as 4 times 10, or 4 tens, or 40, this algorithm on the left, our lattice algorithm, in many ways becomes very procedural. Just add down the diagonals. But why do we add down the diagonals? It's because this first diagonal is our units, the second is our tens, our third is our hundreds, and we didn't have any, but this is our thousands. Right? So I'm going to screenshot that again and not fail this time. There we go. And so this work here has all of the work and kind of some words that go with it. All right, basic multiplication facts. So you know what I'm about to show you next. I'm about to show you your multiplication table. just like our addition and subtraction table, we use these multiplication tables, and how this would actually work in a classroom is you would give it to students, the whole thing would be white, and then once you learn doubles facts, you would give them a yellow marker or crayon, you'd have them color in that square on the right, and then color in those yellow squares on the table itself so that they can start to build in the table as you go. But instead of thinking 10 multiplication facts 0 through 10 times 0 through 10 as 121 different facts, we think of our 0 facts. Anything times 0. If we have 0 groups of anything, we don't have anything. We have 0. So thinking about that as 0 groups. Our ones facts. One group. Our doubles facts is now we have 2, and we start to be able to double quickly. So 2 times 2, 4 times 2 is 8, 2 sevens are 14, 2 tens are 20, and so on. Doubles plus 1, once we know our doubles facts, well, if we had 2 groups of 6 is 12, well, 3 groups of 6 is just one more 6, so 12 plus 6 is 18. So doubles plus 1 set. So that's, I don't know how I want to write it in the general case. I just want to write it as 2 times 6 to 2 plus 1 times 6. That'll work. Red, we have our doubles. So it turns out that doubling tends to be something that children are able to do, and we as adults are relatively quick to do. So 3 times 4 is just 3 doubled is 6, doubled is 12. So it's m times 2 times 2. Our half tens facts, well, maybe it'd make more sense to talk about tens facts. Tens facts relies on place value. Oh my God, there's just never a good place for me to be. I'm going to go up to this corner again. So 10s minus 1 set facts. This is where we have 10 minus 1 times n. So we use our place value fact and subtract 1 off. Double, double, double. If you can double a number, you can double it again, you can double it again. So 6 times 8 is 6 doubles 12, double twice is 24, double again is 28, so 6 times 8 is 48. I said that number wrong. 6 doubled is 12, 12 doubled is 24, 24 doubled is 48. There we go. 6 times 8 is 48 because we double, double, double. And then, so that's just our times 2 times 2 times 2 fact. And then once we have once we have tens facts, we have our half tens facts. Well, 10 nines is 90, so 5 nines is 45. Or 10 sixes is 60, so 5 sixes is 30. And so this is where we half a 10. And then half 10 plus 1 set, that's just where we know, well, 5 times 7 is half of 70, or 35, plus 7 more, 42. Or 9 times 5 is 45, plus 9 is 54. Right, so you can see how multiplication now collapses instead of 121 unique multiplication facts to anything times 0 is 0, anything times 1 is itself. We can double, 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 and double, double, double. Well, once we can double, we can do a double plus 1. And then we can do our tens. And once we have tens, we can do our half tens. We can do our half tens plus 1 set. Or we can do tens minus 1 set, right? And so now it really now boils down to 0, 1s, doubles, and tens. So that's 4 basic ideas with some nuance and addition that give us the entire multiplication table. Formal discussion. So for any whole number, a times 0 is 0. If a and b are whole numbers, then any a times b, 3 times 7, is a unique whole number. It's 21. 3 times 7 is always 21. It's not sometimes 21 or 45. And it's a whole number. So remember, we couldn't do 3 minus 7 or we'd get a negative, which would break our whole numbers. Anytime you multiply two whole numbers, you'll get a whole number back. If a and b are any whole numbers, then we can multiply in any order. And remember, this is where I said we could start to see that if we think of 4 times 3. If we just rotate it, look at it that way, the same number of squares are there, so it must be the case that they're equal. Oh, and here's my 3 times 5 and 5 times 3, right? And so the number of squares doesn't change, so we can multiply in either order. Associativity, that a got pulled up to the previous line. A times b times c is the same as if we multiply BC first, AB first, or AC, it doesn't matter, we'll get the same answer. And you can think of that now not as just an array, but a cube, where we have 3 times 5 times 4. If I would instead slice it vertically into layers, so like slicing it this way, you could see why that would be the same. Or if I would slice it this way, you could see how if I sliced it that way, it would be the same, because the number of cubes isn't changing. So here's the picture. So we could slice it this way, we can slice it this way, or we can slice it this way. Or I guess we didn't slice it at all. They were just too lazy. Slicing it that way. And we also have the distributive property of multiplication over addition. So 4 times 5 plus 2. So we have 4 rows. So these are the rows. That's the size of each row. 1, 2, 3, 4 of them. And we can either think of it as 5 plus 2, or 7, or we can think of it as 4 times 5 times 4 times 2. Right? We can split it apart. And so 4 times 5 plus 2 means we multiply each of those, 4 times 5 plus 4 times 2. And in many ways, I was already using this distributive property when I showed you my partial products, my area model, where I had the 4 squares, and I was doing the 10s, the 10s 1s, the 1s 10s, and the 1s 1s, right? Those 4 squares. I was using the distributive property, but I wasn't naming it. Mental math. The whole reason I go through that formal definition, right, is because as we move on to negative numbers and fractions and real numbers, some of these things like closure will go away. And some of these things, other properties like distribution, may or may not stick around. And so I want us to be able to contrast what we can do in terms of operations based on the set of numbers we're working in. So mental math, place value multiplication. So notice this is really what I was wanting us to do with our standard multiplication algorithm, because we have 4 times 8 is 32, and 4 times 70 is 7 4s are 28, 280, and then we add them. And so when you're doing it mentally, this might be a way to do it. So if you had 78 times 4, you might do 70 times 4 plus 8 times 4. But notice, what is that really? Well, that's really just 70 plus 8 times 4, and we distribute, right? So the distributive property we give a name to because it ends up being very, very important to our concept of multiplication. Compatible numbers. So I have 2 times 8 times 5 times 40 times 5. Well, I might be like, well, I know that 2 times 5 is 10, and so that's a nice, neat number to work with. And 4 times 5 I know is 20, but that's 40. So now I have 10 times 200 times 8. And we could do some number of multiplication that way. Typically, you're going to stick with place value 2,000 times 8. 8 times 2,000 is 16,000. And that's our answer. And so being intelligent in how we choose, and this is one of those things that comes up as we get more comfortable in terms of thinking about our tens facts and our doubles and our half tens and things like that, gives you a way to work through those. Thinking money. So if I have 84 times 25, often if we think about 25 as being a quarter, we have 84 quarters now. And we know that every 4 quarters is $1 or 100 cents. And so it's how many dollars are there in 84 quarters? Well, we know there are 21 of them because 84, well, we take $1 off. And then I have 80. And so I know that 8 quarters is $2. And I have 10 groups of 8 quarters. So 10 times 2 is 20, plus 1, 20, plus 1 is 21. Even then, you might not want to do that one in your head. You might also do it a different way. Once you think about 25 as being a quarter, you could just say, well, that's a quarter of $1. So a quarter of 8 is 2, and a quarter of 4 is 1, 21. Right? And so thinking it that way. But when you're working with smaller numbers, thinking money, so more like what we're thinking, maybe like, my pen went away, 17, that was 25, right? You might use it a little bit more there because the numbers are more manageable. And now you say, well, I know I have 4 quarters gives me 16, and I have 1 left over. And so I end up having 4 times 100 plus 25. And I definitely made a multiplication mistake there. Like, I don't even have a doubt. 17 times 25. Oh, and I didn't. Look at that. Sometimes our gut leads us astray. Sometimes we're like, that's definitely not right. And here it was. So spend some time thinking about multiplication. I hope that at least part of this made you think about something that maybe you took for granted a little differently. And maybe when you think about m times n equals p, groups times a certain size giving a product, you might appreciate some of the interesting parts of multiplication of whole numbers. See you in the next video, everyone.